Hello and welcome to analyticseducator.com. Today I'm going to show you some of the statistical tests which usually we do in statistics, like t-test, ANOVA, chi-square, correlation. So I'm going to tell you about this test, why we are doing this test, what is the purpose of these tests, and then I'm going to show you how to do it in R, and I'm going to tell you about the interpretation. So let's start. We'll start with a t-test. T-test means, by definition, it's a type of inferential statistics used to determine if there is a significant difference between the means of two groups. For example, what does it do? If there are two different companies like TCS, okay, and IBM, and I want to know which of these companies are a better payer, which company pays more. Okay, so what usually I will be doing, I will be taking few different employees from TCS. Okay, somebody gets 10 rupees, just an example. Somebody gets 12 rupees, somebody get 30 rupees as their salary, suppose. Okay, some gets 40 rupees. Similarly, in IBM also I'll be having different people, 14 rupees, 5 rupees, 19 rupees, okay, 33 rupees. And what I can do, I can take an average out of it. Simple. I can take an average of both the groups. In this case, I can see TCS is more, but this is not a proper test. The reason being, this is just a sample. It might so have happened that I have taken maybe the senior management from TCS and the junior people from IBM, right? So what if I do this test once again? I take some other sample. It might so happen that I get a different result. This time TCS might, the average might be 10 and IBM might be 15. So in this case, IBM will be more. So what if I do this test 100 times? Out of 100 times, if I see that probably 95% of the times out of all these 100 tests, TCS is having higher salaries than IBM, okay, then 95% of the times I am seeing that TCS is more than IBM, then I can say, okay, it means TCS is having higher salary than IBM. Okay, this is called a hypothesis testing. Usually we take this confidence like either 95% or 90% or 99%. Usually these are the three values with which we do the statistical test. Okay, for the time being we will be taking 95% for all our following test. So how to do this in R? Let's say I have a data set. Okay, there is a company called Arindam Incorporation and I have their HR data. This is my data set. You can see. Let me increase the font little bit, it will be easier for you to see. Okay, now over here I have their age, gender, these are all self-explanatory. Country is always, I mean, all are India. Some of them are India, Australia, France, Israel, Poland, Saudi Arabia, different countries. People are, I mean, it's just a multinational company or in the incorporation. So they have branches and offices in different cities. They have departments, different positions, and their salaries. Okay. Now, in t-test, what I am going to do is I want to understand whether there is any bias in this company or not. I mean to say whether male are getting higher salary than female or vice versa. Do you have any discrimination over here? This is what I want to test. Okay. So then what do I need to do? First I will import this data set. I will copy the path and I will put it over here. In case you are new in R and you do not know about this R coding, then I'm going to create another video where I'll be teaching you how to write codes in R. But for the time being, my assumption is you already know little bit of R coding. I will install a library. I will simply import the data set. I named it as rock. So this is my data set. I have salary, I have gender. Now I'm going to do the t-test, with which I'm going to understand whether male and female are having different salaries. Okay, is there any significant difference or not? So how to do that? Simply you can write t.test, then out of these two variables, salary and gender, salary is my numeric variable. So the numeric variable I need to write first salary, then give this sign tilde. Always remember R is case sensitive. In my dataset S is capital letter, so I also should be writing it in capital letter. It's better if you just copy paste it. Simple copy it and paste it. First the numeric variable, then the grouping variable, and then data equals to rock. This is the name of my dataset which I had named it, and you simply execute that by pressing Ctrl R. This is the result. In this result, so what I should be checking? I should be checking the p-value. Okay. Now in hypothesis, the null hypothesis says there is no difference. An alternate hypothesis says there is difference, means there is a difference in the mean of the two groups. Two groups are gender, male and female. So my p-value is definitely more than 0.05, which is my level of significance. Okay, if it is more, then I will say I fail to reject the null hypothesis. That means I will conclude there is actually no difference. Male and female are getting same equal amount of salaries. Statistically there is no difference among male and female. That means it's a company, ethical company, which does not discriminate among the male and female. Alright, there is another way of doing the same t-test. So you can also do it in this way. Either of the way will work. So over here I simply used the grouping variable, the single variable which is male and female. Alternatively, I could have saved the results in a different variable, like all the salaries for male, all the salaries for female. Like this is a filter. Gender equals to male and the column is salary. I save it as SM, salary male, and then I similarly save it as salary female, all the salary for the female. It's a normal filter condition. Again, I'm telling you, if you do not know this, I will be taking another session where I'll be teaching you all this R coding part only for the new people. The advanced people, you already know this. Then I will be doing t-test, just these two groups, SM and SF, and I'll be getting the same result with the same interpretation. Alright, now so much for t-test. In this t-test, what we did, we took two different groups, okay, which has two different population. Now it might so happen that we do a paired t-test. Paired t-test means we do the t-test, we do the test on the same dataset or on the same sample. For example, suppose there is a company which says they have invented a tonic. okay, suppose which cures the coronavirus. Now I have taken different people. I mean, just imagine these are the people. Now I have given this tonic to them, which claims that it's going to cure the coronavirus. Now what happens? I will be having some before before the tonic were given, how was their health? And there will be an after effect after the medicine has been given, how is their health? Okay. Or let's take another example. Suppose it says that it's going to increase their body weight. So before the weight, probably they will be having some weight, some random weight I have taken. Okay. And after the tonic, they will be having different type of weight. So I want to understand, on an average, does it help them to increase their weight, which the tonic claims? The tonic says it will increase their weight. So does it help? So there again has to be a statistical uh, test, because I can see these guys weight has increased, but it could be just by chance, may not be due to the effect of the tonic. But then we do a test to understand. If the test says there is a significant difference, then we'll understand it is due to the tonic. So how to do that? Again, I have another data set with the group. These are the weights what people had before the tonic, and these are the weights of the same people after they had consumed the tonic. Okay, so we are doing the test on the same samples. So let's see how we can do that. First, I will read that data sheet and I will save it in the name of a cane. Okay, now again do the t-test, the numeric variable, that is weight, then tilde, then the grouping variable group, and the only difference will be you need to write paired equals to true and data equals to cane, because I saved it as cane. Let's execute that. See, the p-value is less than 0.05. It's e to the power -0.09. It means first we will be 0 point, then we will be writing 9 zeros and then 62. Okay, this is how we are going to write it. This is how. That means it's definitely less than 0.05. If it is less than 0.05, then I reject the null hypothesis because my p-value is less than 0.05. Again, if you are new to hypothesis testing, I will create another session on hypothesis as well. You may go through it and you will be able to understand what I am talking. And with the new videos, I'll give you the link in the description. So for the time being, so p-value is less than 0.05. That means we are going to reject the null hypothesis. So that means we decide there is a difference, okay, among the groups with the before and after. Now the question comes, how do I know whether the weights have increased or decreased? Right? For that you need to check the t-test, t-value, the t-statistics. It is in a positive one. If it is positive, then that means it has increased. If it is a positive, that means among the averages, whichever is high, that will be of higher value. Or in other words, just imagine I check the weights of the two different groups. After is higher than the before one and the t is positive, that means after group has increased. Had the t value been in negative, this would have been reversed. The meaning, it's positive, that means after group has increased because their average is higher than the before group. Okay. Alternatively, you can also do this, that if you want to understand whether the average weight before treatment is greater than the average weight after one. So I can again do a t-test, weight group data can pair true alternative equals to greater. You can also do this. See, p-value is less than 0.05. That means it is significant. Let's check the hypothesis. It is p-value is less than 0.05. That means I reject the null hypothesis. That means there is a difference. That means the average weight before treatment is greater than the average weight. That means in after weight it is greater than the before one. And if I do the same thing with the less, p-value is 1. That means I fail to reject the null hypothesis. That means actually it is not less. If you are feeling this is too complicated, usually we don't use it. Simply do this t-test, pair t-test, and then check the aggregate. If t is in positive, then whichever is of higher value over here, like after is of higher value the average, that means it is greater than the before group. It is significant. Alright. Now we will do ANOVA. ANOVA is, it is just like a t-test, the same thing, but it is between 3 or more groups. T-test is only applicable on 2 groups. It cannot be done on 3 groups. But whenever you have 3 or more groups, then we use ANOVA. Now let's see how to do ANOVA. Now with the same data set or in the incorporation I will be doing. This time I'm going to check, do you have any difference in the department? Like engineering, sales, I have different department, right? I have different departments: admin office, executive office, ITIS, production, sales, software engineering. So what I want to understand is, do they earn, all of them earn exactly the same way, or there is a difference in their departments? So I have more than 2 groups, that's why I'll have to use ANOVA. ANOVA is very similar to t-test, the coding part. So you write AOV, the short form of ANOVA. First you write the numerical variable, that is salary, then the grouping variable, that is department, data equals to rock. It's executed. With summary we will get to see the result. In ANOVA again, if I tell you the hypothesis, the null hypothesis says all groups are same. Alternate hypothesis says at least one group is different than others. Okay, so we will check the p-value. It's definitely less than 0.05. So we will reject the null hypothesis, that is all the groups are not same. At least one group is different. Okay, so what I understand is, out of them at least one group is different than others. It might so happen that 2 groups are different from others. It might so happen that all of them are different, but it says at least one of them, but it doesn't tell me which is equal and which is different. In order to understand that, we need to do a Tucky test. In Tucky test, it's going to compare the pair-wise department. I will show you. Tucky HSD, this is the code, and Boogeyman is where I saved all the results. if you see this result, check the p-value, okay, and the pair. Executive office, admin office, the p-value is less than 0.05, that means they are significant. It says there is a significant difference between executive office salary and admin office salary, okay. Production admin office, p-value is more than 0.05, that means there is no difference in salary between production and admin offices. They are earning kind of same thing. Sales and admin office, p-value is less than 0.05, so there is a difference, okay. Software engineering, ITIS, it's more than 0.05, no difference. Similarly, you can understand where there is a difference and where there is not a difference. Alright. Now there is an assumption of ANOVA. The assumption says among all the groups their variance should be of equal. The variance should be of the same variance, equal variance. And how do I test that? For that we have a Levin test. For that you require a package which is library car, and then you do Levin test, then just write the same format, salary department data equals to rock. Again over here the 80, the null hypothesis says equal variance, and alternate says variance are not equal. At least there is one group which is different from others. So if you check the p-value which is less than 0.05, it means I reject the null hypothesis. So we say the variances of all the groups are not equal. It means it violates my assumption. Then what do we do? Okay, there is another assumption that my residuals should be normally distributed. This is another assumption. How do I check that? You write residuals, object equals to boogeyman, because I saved everything over here as boogeyman in my ANOVA. So I am saving all the residuals as Goldberg. I want to check whether they are normally distributed or not. I can check it with Shapiro test. The p-value is again less than 0.05. Over here the null hypothesis says data is normally distributed, and the alternate says data is not normally distributed. So it is less than 0.05, that means I reject the null hypothesis. I say the data is not normally distributed. I can do the same test with Anderson-Darling test. For that you require another library, NOR test. You write AD.test within bracket Goldberg, where you have all the residuals, which again says the same thing, it's less than 0.05. See, these are the two different tests. Both are for testing normality test. Both may be giving you a different p-value, but always their direction will be same, because over here both are telling you they are not normally distributed. So we understand that my assumptions are violated, right? So what do I do now? When my assumptions are violated, then there is a non-parametric alternative which is called Kruskal-Wallis rank sum test. Okay, with this test usually we do when my assumptions are violated, like normality and homogeneity. These tests are violated, we do this Kruskal test. You do the same test, Kruskal.test, salary department, salary is the numeric variable, department is the grouping, data equals to rock. Now you are getting an error. Why this error you are getting? Because sometimes it might so happen, if you check the rock, my department is character, so we need to change it as factor, and then you do the test. This time it's not going to give you an error and it will give you the result. P-value is less than 0.05. Again we do the same hypothesis just like ANOVA. If it is less than 0.05, we say that we reject the null hypothesis which says all the department salaries are same. but there is a difference in their salaries. Okay, next is we have done till ANOVA. Next is a chi-square test. Chi-square test is, it's a non-parametric test. That means it doesn't require the assumption that your data is normally distributed. This tests whether you have any dependencies among any categorical variable or not. Okay, now for example, in an engineering college or maybe in an university, there are different students, maybe arts, commerce, science, and there are different laptops which have been provided to them. Windows and Mac. Now I want to understand, do I have any relation? Like if you are from a science department, you mostly prefer Mac. If you are from commerce or arts, you mostly prefer Windows, or there is no connection. It doesn't matter whether you're from arts, commerce, science. So on a random basis, people prefer Windows and Mac. So this is what I want to understand. Do I have any relationship among them? Among the categorical variables. Over here, all are categorical variables. In t-test and ANOVA, we used to have one categorical and one numerical. Over here, all are categorical. Okay. Now, let's do it. I will install the library mass. There is a inbuilt dataset called survey. In survey, I have uh, about the feedback of some people who have done exercise and smoking. It means we have 11 people who smoke heavily, 189 people who has never smoked, 19 guys who occasionally smoke, 17 guys who regularly smoke. Similarly, I want to do it with exercise, frequently, sometimes, and never. So if I create a table out of it, okay, there are 7 people who smoke heavily, and frequently exercise. There are one guy who smokes heavily and never exercises, never does any exercise. Okay, then 12 people who smoke occasionally and frequently exercise. So this is the table. So in this table, I want to understand, do I have any dependencies among these categories? So let's check. So how to do that? I write chi-squared dot test within bracket Kane. So I save it as Booker T. So the p value says it's more than 0.05. Again, over here, the null hypothesis says they are not related. Alternate says there is a relation. So it's more than 0.05, so I fail to reject the null hypothesis. Okay, so I say they are not related. Okay, that means whatever you have, there is no dependencies among them. Okay, now you might have noticed I got a warning message. I got a warning message because in some of the columns, so I have the values which are very less, like 1, 3, 4. So what I'm going to do, I'm going to just add up these two columns and I create it just one. and then I do the test. So C bind, Kane frequency, and Kane none and sum. I'm just adding them up and I'm saving them as Undertaker. Okay, now if I do the chi-square test, I don't get any warning message. Okay, and the p-value remains same. There is no relationship. So in case of a warning message, it is due to insufficient data, but in your real life you will be having lots of data, so don't worry about the warning message. Let's do another one. I have a data set, house task. Let me import the data and I'll explain this to you. And I'm saving it as Kane. See over here, I have different frequencies. Laundry, it has been done 156 times by the wife alone. Alternating, that means one day the wife is doing, another that the husband is doing. 14 days they have done it 14 times. Husband alone has done it twice. Jointly they have done it 4 times. Main meal of the day, 124 times it has been prepared by the wife. 20 times they have done it on an alternate basis, 5 times by the husband, 4 times jointly. Similarly, we have it repairs, holiday, insurance premium paid, finance, driving, all these things. So again, I want to understand, do I have any relation among them or not? So let's do that. Again, chi-square test, Kane. This time the p-value is less than 0.05, so we understand there is a difference. I mean, there is a relation. They are related. But let us understand how they are related. If I write Booker T dollar observed, that means it's going to show me the raw data which has been observed. If you want to understand the expected, because here the null hypothesis says there is a dependencies, there is a relation. What if I wanted to see the data, there would not have been any dependencies? Then you can write Booker T dollar expected. Had the data been like this, then there would not have been any dependencies, but it's not required to do by you. Just I wanted to show you, that's it. Now let us understand the residuals. With the residuals we can understand where there are dependencies. You can write Booker T dollar residuals. See, higher the values, there are dependencies. Laundry and wife, that means mostly the wife is doing the laundry. They are related. It can be checked in a better way if I visualize it. For that you require this library correlation plot, and check this plot. Whether they are the blue ones, if the sizes are higher, the dependencies are more. And this cream or yellow or red, whatever you want to call this one, I'm pretty bad with my color senses. They are not associated. They are not related. So maximum relation I can see repair and the husband. So mostly the husband, he does all the repairing work in the house. Holidays jointly. Laundry and main meal are done by the wife. You can say followed by dinner and breakfast. Laundry and the food are taken care of by the wife. And all these things, they are not associated. They are not associated. Driving, official, they are not as correlated as the repairs, but still there are dependencies, but mostly they do it by alternating. Okay. Now it can be done in a better way, because in this one we also have something for the not related parts which might be confusing. So if I do this one, I want to see only the relationships. Only the relationships. So it has a positive relationship, husband and the repair, and the followed by holidays jointly, and laundry by the wife, and main meal by the wife. Rest are not so significant. Only these four are mostly significant. Alright, I have also written it. Wife is strongly associated with laundry, main meal, and dinner. Husband is strongly associated with repairs, and jointly they are with holidays. This is how we can understand. This is for about the chi-square testing. I mean, this is here is another example which you can do it as your homework. It's a very small data set. Whether gender influences a person to check the TV shows. Do you like wrestling, WWE wrestling, or TV serials like drama? Men, 309 men like WWE and 80 men like serial, 25 men WWE and 448 men women like TV serial. Okay. So does the gender affect the TV show? So you can do a chi-square test in order to understand it. Our last point is, or the topic is, the correlation. Correlation means, again, it's a relationship between two numeric variables. In chi-square we were doing with the relationship among the categorical. Here we will be doing the correlation among the numeric. For example, if I have two different data sets, maybe X and Y. X is maybe 1, 2, 3. Y maybe 30, 20, 10, or maybe 10, 20, 30. So I want to understand, do they have any correlation? It means when X is increasing, Y is also increasing. Yes, we can see that. And if X is increasing, Y is increasing in exactly the same proportion. So if I want to check their correlation in Excel, so you can write correl, just select them. It's +1, means they are positively correlated, means if one X increases, Y also increases. Okay. Had it been like 30, 20 and 10, your correlation would have been -1. Still they are related, but inversely related. When X is increasing, Y is actually decreasing. So correlation ranges from +1 to -1. Okay. And if the situation is like this, that means when X is increasing, there is no relationship on Y, then correlation is 0. So we can do this using R. How to do that? Suppose we have an inbuilt dataset, empty cars. I save it as Joita. Okay. Over here I have the weight of different cars and the miles per gallon of different cars. I want to understand, do I have any correlation among the miles per gallon and the weight? Let's check. Okay, before that, for correlation we have a assumption that they should be normally distributed. So let's check that. Shapiro test or Anderson-Darling test, both are telling you p-value is more than 0.05. That means they are normally distributed. Let's do that for weight. Again, both are having p-values of more than 0.05. That means they are normally distributed. No problem with that. Then let's do it. There are three types of correlation test. One is Pearson. You write COR, C-O-R, Joita dollar weight and Joita dollar MPG. Method equals to Pearson. It tells you there is a negative correlation, means when one increases, the other decreases, which makes sense, because if your weight of the car increases, the miles per gallon decreases. The fuel efficiency will go down. There is also a test, hypothesis test. Over here, the hypothesis, null hypothesis says there is no correlation. Okay, they are not correlated. And the alternate hypothesis says there is a correlation. So because again we have doing it on a sample. So what if we had done it on the population, on the entire car of weight? Okay, if I taken it on the population, then whatever we are getting it over here, would I have gotten the same result? That's why we do the test. If the test is significant, then we will say yes, I would have gotten the same result if I had done it on the entire population as well. So you write core test, rest are same. Just execute that. P value is less than 0.05. Okay, that means I reject the null hypothesis. That means I say there is actually no correlation. If I had done it on the entire population, I would not have gotten this result. But for this sample, the correlation for this sample, if I take, if I assume this is my population, then there is a correlation. Now, I said they should follow a normal distribution. They are following a normal distribution. But what if had they not been following a normal distribution? Then I would have done a different sort of correlation, which is a Kendall rank correlation. So the correlation would have been the same thing, exactly the same code over here. Instead of Pearson, it would have been Kendall. You can do the test, core test method equals to Kendall. Over here, see p value is again less than 0.05. I reject the null hypothesis. Tau is the Kendall correlation. It will be slightly different than the Pearson. And you do it when they do not follow a normal distribution. Similarly, you have another one as Spearman rank correlation. It also done, usually we do it when the data do not follow a normal distribution. Over here, the RHO, this is your correlation. But again, the p value is less than 0.05. That means they are saying, had it been done on the population, we would not have found this correlation. This is my correlation. All are negative. That means when one increasing, the other one decreases. Okay. I hope you have understood something in this video. Thanks for watching this video, and do let me know if you have any question. You can write it in my comment box. Please do subscribe our channel, and you may visit our Facebook page as well. You may visit our website as well. We have lots of courses. If you want to enroll or you want to know anything about that, please free to write to us. Thank you so much for your time.